The geographic and location datasets to be used in this trace stream network for pollution study has already been pre-packaged into a geodatabase zip file, which houses all the information. We'll extract the content from the zip file and then run ArcGIS Pro. ArcGIS Pro is a GIS software. GIS stands for Geographic Information System. These are advanced mapping softwares where we can perform location analytics and visualization workflows. ArcGIS Pro is built by Esri, which is the world's leading GIS developer. We'll open a new project in ArcGIS Pro and name it as what we like. I have named it as Ashokan_stream_trace, and the map view opens in front of us. Ashokan is a name of a reservoir which lies in the New York State on the eastern coast of United States. This reservoir supplies water to the world famous New York City. Next, what we will do is to add the geodatabase which we had extracted into the software. So from the catalog pane on the right, we search for the location where we had extracted the geodatabase and then open the .gdb file. The geodatabase has been added. Now let's examine the area of interest closely. We can search for any location by using the locate command. Yes, the blue dot indicates the location of Ashokan Reservoir, which is that large blue spot in the center of the software. Map view. A reservoir acts as a repository of water. You can very well imagine that to run an urban megapolis such as New York City, one would need large quantities of water as well as a steady supply of it. It is with this intention that this particular reservoir was artificially constructed in the early 1900s. In our geodatabase, there are three particular files: the Ashokan_stream file and the permitted discharge origin and the storm drain files. I'll explain it one by one. So first let me open the streams file. In our map view, you can see a number of streams. These act as a source of water supply to this particular reservoir. Let's change the base map to terrain view so that we can understand the topology of the surface a little bit better, and it will give more context to this study. The reservoir is surrounded by hilly and mountainous terrain. So the streams typically origin at the top of these particular landmass and then flows downwards into the reservoir. And as you are observing, there are a number of streams as well, and they are interconnected in nature. So this is a complex, you can say, water body in terms of its supply of water. And you can understand that because water is such an important topic, one needs to safeguard the health of the water system, which is one reason why we are doing this particular workflow, to understand how this particular topic can be effectively dealt with. Because this is a data set, we can see the data points in this particular data set by opening the attribute table. So the attribute table of Ashokan streams contains a length parameter which tells you that what are the length of each individual streams. As you can see, each stream on an average is 400 meters or 0.4 kilometers long. There is also a flow direction, and for each of the 886 streams which are connecting the reservoir, they basically have a flow direction of 1. What does this essentially mean? It means the way in which the streams were digitized is also the way in which the streams flow in real life as well. So for example, if I have digitized a particular stream by drawing a line from east to west, in real life also that particular stream flows from east to west. Our entire network comprising of 800 plus streams were digitized in that way. Next, we've loaded the storm drain origin dataset onto the map view. We will adjust its symbology so as to make it much more visible and prominent. As you are observing, it is on the eastern side of the reservoir. What is this point all about? Let's assume that a nearby resident had observed that the color of this water in this particular stream is starkly different than what it used to be and notified the authority. So this point acts as the spot where the pollution was initially observed. Next up, we will load the final layer, which is the permitted discharge or origin layer. We will adjust its symbology so as to make it slightly distinct compared to the previous data set. As the name suggests, this particular layer is a location where the pollutant was allegedly introduced into the system. So let's say the authorities conducted their investigation and found that some mischief maker had put in some pollutant in the water body at this particular location. So the objective of this study is to determine the extent of contamination as well as the extent of possible contamination before corrective measures are undertaken. Firstly, we will create a new empty dataset. We will call this dataset Ashokan Streams Dataset, and in the environment section, we will just ensure that the output coordinate system matches our default Mapviews coordinate system. This will ensure that the visuals are consistent and geometrically accurate. Once this feature dataset has been created, we can see that it is housed in the same geodatabase which we had loaded at the beginning of this study. Subsequently, we will add information to this empty dataset. The most important information is the streams layer. So we've used the feature class to geodatabase command to transfer this particular layer into this empty dataset. The next step is to create the trace network. What is a trace network? A trace network will tell us how the streams are flowing. What is their starting point? What is their ending point? What is the length of those streams? And what is the direction of the streams? This information is already available to us, but then we will now see a map-based depiction of this. We've run the geoprocessing tool with a simple edge input edges parameter. What does it mean? It means that the tributaries of the streams are non-existent, as in that the streams have a distinct starting point and a distinct ending point. On the left of your screen in the contents pane, the output has been created. The hydro trace network is what we named our trace network diagram, but then the output is still not changed. Just what we see is a purplish translucent hue across the map view. This is because we have not enabled a network topology in this particular trace diagram yet. So first we will add a network attribute. So if you realize that in our stream layer we had the length of the stream as a parameter mentioned. So this is the network attribute which we will use, because currently the software does not understand where the particular line is starting, where is it ending, are two lines connecting with each other, or is there any error, which is why the entire purplish hue is there, which signifies that the network attribute is either incorrect or missing. It is missing in our case, that is. So in our network attribute, we will set the length _ kilometer from our original stream dataset as the parameter. Once this network attribute has been set, we will enable the network topology, and then the output of the trace network diagram will be distinctly visible to us. In the input trace network, we've selected our trace network diagram, which is hydro trace network, and all we need to do is to run that command straight away. as you would see, the purplish hue is eliminated, and now what we have is a starting point and the ending point of each streams. The directionality information and the length information is also available, but then it is not something which is visually observed. We have to open the attribute table to understand it. Let's focus our attention on the region where the pollution activity was spotted. The red colored storm drain origin point is not part of a trace network yet. For us to do any subsequent analysis, we'll first need to make it a part of the trace network. An easier way to do so is to manually draw this point. The green colored circle lies on top of our trace network diagram and will act as a substitute for the original location. Once the point has been added in the trace network, we will click Upstream, which will open the trace command in the geoprocessing toolbox. This command will help us to fulfill the first objective of our study, which is to identify the streams which lie upstream to the point where the pollution was initially spotted. Just be aware that initially we are not setting a filter which will isolate the streams which lie between the red spot and the green spot, which lies between the spot where the pollution was initially spotted and between the spot where the authorities suspect the pollution to have entered the system. Currently we have not set that filter. So the blue lines which you are seeing depict all the areas which lie upstream, which some of them lie even upstream to the alleged area where pollution entered the system. So this is the first step of the workflow. Subsequently, we will modify the trace command to include the particular green spot also. But currently what we are doing is to save our results as a separate layer, because we are not just interested to visualize the output on a map, but we also want to see the data set for ourselves to understand what is the length of the streams which have been affected, what is the, you can say, number of streams which have been affected, and so on and so forth. One can play around with the color combination as well. I am changing the appearance of this upstream layer into a more prominent shade of blue. Let me close the hydro trace network diagram so as to make the map view less cluttered. The blue lines which you are seeing are the streams which lie upstream to the red spot, which is where the pollution was initially observed. And the tiny green circles on the blue streams are the starting and ending points of the streams themselves. Next up, I will show you a more technically accurate way of doing this upstream calculation. If you remember, initially I had drawn a green circle manually besides that red spot. This may not be a very precise way to do so. So first up, we will use the copy features command to create a replica of the storm drain origin red spot. This is a precautionary step. I am doing so just so as to not to tamper the original data set. So once this replica has been created, I will run the snap command on it. This is an important command which will allow us to do this workflow in an automated way. So what we are essentially asking snap command to do is to find the spot on the trace network diagram which lies 50 meters away, not more than 50 meters away from the red colored storm drain point. So this is an automated way, and the software will automatically find a spot which lies on the trace network diagram and not exceeding 50 meters away from the red spot. And this point which it will find, it will automatically add it as a new point rather than us manually drawing it. So when we had manually drawn that point, it could have been 100 meters apart, 200 meters apart, and the results would not have been technically accurate. And this is a matter of water health and public safety. So we need our analysis to be much more precise. So this is why the benefit of using the snap command. So similar way, now we are basically using the snap command to convert the permitted discharge origin point, which if you remember is the point where the authorities suspect the pollution to have originated. So we will use this particular command snap tool to link this point, green point, which is currently as a separate layer, to the trace network diagram in an automated way. Now that we have our more precisely located storm drain and permitted discharge point ready, we can rerun the upstream workflow using the trace command. We will do so, but this time with a small tweak. When we ran the tool first time, we did not include any barrier point. But this time we will include the green colored permitted discharge point as the barrier. The permitted discharge point is where the authorities assume the pollution to have entered the water system. So essentially what we are doing is running a second scenario. The first scenario was a worst case scenario wherein all the areas which lied upstream to the observation point, which is the red spot, were highlighted by the software. This time around, only those streams which lie between the red and green spot will be highlighted in the system. So scenario analysis, as you would understand, helps in planning, and in this particular case the authorities can understand what is the difference between both the scenarios, and the amount of effort in remediation will vary accordingly based on which scenario is accurate. When we open the attribute table, we can spot that there is 8.5 kilometers of streams which are impacted by the pollution if we were to assume the worst case scenario. But if we were to assume the less worst scenario, it is 6.5 kilometers. Now both these figures are high, but then there is a significant difference between both the scenarios as well, as in there is 2 kilometers less pollution, and if true, then it will be much more beneficial as well. We will do the downstream trace analysis with a view to fulfill our second objective, which is to identify the risk and extent of streams which can be further impacted from water pollution in the future, now that we have observed the pollution which is highlighted at the red spot. So the methodology largely remains the same. We will just select the downstream type of trace. This time around, the scientists have conveyed to us that because the polluted water has traveled to a distance of 6 to 8 kilometers already, it has become diluted as it interacts more with fresh water. So the further risk of contamination would be restricted to a maximum distance of 500 meters of stream length only. So how do we input this particular information? We will add a functional barrier and ask the software to only depict those areas downstream which lies not far away than 500 meters of stream length. Once we run this command, the highlighted area appears on our map view, which is our downstream trace analysis. I hope you found this risk assessment water workflow to be informative. It will demonstrate to you the power of location analytics and visualization as we have observed on ArcGIS Pro GIS platform.